Next, let's consider this example. Here I have a molecule with, again, 2 chiral centers, because if you look at either of these carbons, the carbons are bonded to 4 different groups. 2 to the 2 is 4, which, remember, that's the maximum. So we could certainly have less than 4, just not more stereoisomers for this molecule. Let's do like we did in the last example and draw all 4 possibilities. Possibility 1, we'll put both chlorines out. 2, let's put them both back. 3, 1 out, 1 back. 4, 1 back, 1 out. So these are the 4 potential stereoisomers. But what you want to recognize is that if we look closely at these first 2, let me take this second one, and I'm going to highlight that carbon just to give us a reference, and flip it over horizontally. When we flip that over, we flip that carbon from the left to the right, and that makes our chlorines come out by flipping it over. Okay, now compare it to, let's just do A, B, C, and D. Compare that to A. And these certainly are mirror images. The problem is, even though they're mirror images, they're superimposable. You could take B, pick it up, set it down on top of A, and they would superimpose. They're identical. For that reason, these are non-enantiomers. But they're identical compounds. So if you think about this, A is superimposable. On its mirror image. B. If that's the case, A and B don't have an enantiomer. If there's no enantiomer, it must be achiral, because chiral molecules have enantiomers. Achiral molecules do not. So we'll say those are achiral. A equals B. And this leads us to kind of a new point or a new term here. If we have a molecule that has 2 or more chiral centers, it can actually be achiral due to a plane of symmetry. So in this case, because those chlorines are on both sides, there's a symmetry plane that'll cut this molecule in half. And this type of compound where you have chiral centers, yet it's achiral due to symmetry. This is called a meso compound.